Hello, everyone. This is Fanny Zhang from IMSC. It's my great honor to introduce our speaker, Professor de Koster, today. Professor de Koster is a professor of logistics and operations management at Rotterdam School of Management, Erasmus University, and he chairs the Department Technology and Operations Management. He holds a PhD from Eindhoven University of Technology, and he is the 2018 honorary Frank Key Professor at Hasselt University. Professor De Costa's research interests are warehousing, material handling, and behavior operations. He is a founder of the Material Handling Forum, and he is the author or editor of 8 books and over 240 papers in books and academic journals. He is associate editor of Transportation Science, Service Science, and Operations Research. Let's look forward to Professor Da Costa's seminar.
Thank you very much for this very nice introduction, Fangni and Johan. So I'm happy to share my screen with you. Is it visible for everyone, my screen?
Yes, we are looking at the browser.
Okay, great. So you're looking at my my presentation, right?
Right now,
It's the browser.
Oh, I shared the wrong screen. I'm very sorry. Share again. So this one should be good. Better?
Yes, this is perfect.
Great. Thank you very much. So the topic of my talk is on warehouse robotics. And what I want to do is with this talk, I want to share with you two things. One is some of the developments we have seen in practice lately with respect to new types of systems. And second, I also want to share with you some of the research we have done. So it's not that I'm going very deep in any of the papers. I just want to touch on some of the subjects we have been studying. And also I want to set some guides for how to continue research in this, in my view at least, very exciting area. So this is what you might think of when you think of warehouse robotics.
And we've been saying, how close to human levels of performance and speed could we get in an ordinary task like moving boxes around on a conveyor? And we're getting up to about 2/3 of the speed that a human operates on average. And this robot is using both hands, it's using its body, it's stepping. So it's really an example of dynamic stability, mobile manipulation, and mobile perception. Here, we actually have 2 atlases. Now, everything doesn't go exactly the way it's supposed to.
So this is, of course, not what we have to think of when we talk about warehouse robotics. These are nice developments by Boston Dynamics. But if you talk about automated warehouses, we typically look at other types of systems. So these are the systems you might find in these highly automated warehouses using robots. So this picture comes from a paper we recently published in Transportation Science, a review paper, which basically reviews all kinds of robotic developments that you find nowadays. So the first system is called, these are the so-called AVSR systems. AVSR stands for Autonomous Vehicle-Based Storage and Retrieval Systems. So basically systems with shuttles. Then the second type of papers, and also the ones that I want to talk about, are so-called puzzle-based systems. Puzzle-based systems are systems where items are stored very dense with very little space in between, and where still every individual item can be retrieved by the system. Then another developments are so-called big support robots or big support automated guided vehicles. So these are basically systems where people work together with the robots. And then another development is sorting systems. So as you can see, these are just a couple of systems. There are many more, but this is what I try to cover in today's talk. So the program is as follows. I start with robotic warehouses to give you some examples of fully robotic warehouses even. Then the shuttle-based systems called AVSR, autonomous vehicle-based storage and retrieval systems. This is a picture of that. Then the pick support robots, pick support autonomous mobile robots. Sometimes these things are called cobots. Here you see a picture of that. And then compact storage and sorting systems. Here you see a picture of that, and then I'm going to wrap up. So why do companies invest in automation or in robots? Well, there are several arguments you can find that might hold in practice, and these arguments have to do with cost, obviously. So reducing operational costs, reducing cost of labor, 24/7 operations. The second one has to do with space, and the space is also has to do a bit with cost also. So if you use a high level of automation, you can basically shrink the space in which you can do the process. And space is very expensive. You have to think of large warehouses where a large part of the cost is not determined only by labor, but also by the space it consumes. And of course, it also gives you some better control, leading to fewer errors and things like that. To be honest, all these arguments are valid, but I don't think they are the real most important arguments. When I talk to companies, the most important argument they give me is, we cannot find the labor force anymore, willing to do the work 24/7. So yes, the labor is available at some hours, but not at the hours we want them, not always, and insufficient. So we cannot rely on labor anymore. This is particularly true in the Netherlands, for example, where I'm from. Labor is a scarce good, particularly at, you might say, outside office hours. So this is one of the reasons that some companies start automating. Now, if you look at the type of warehouses that use these robots, one big user of these robot warehouses are these companies. This is Edna, a wholesaler in Germany. This is a Coop, a grocery retail chain in Norway. This is Albert Heijn in the Netherlands, where I'm from, also a grocery retailer. And this is JD.com in Shanghai. So you find very nice videos of these companies on YouTube. So for example, a nice video of JD.com on YouTube. So these warehouses are fully automated, meaning there are people in these warehouses, but the major processes from incoming goods to outgoing goods are automated, are done by robotized systems. So how do these warehouses work? This is a flow diagram of a typical warehouse. For example, the warehouse of Coop in Norway operates like this, and the same for Edna and Albert Heijn. They work like this. So these are all retailers or wholesalers, but particularly for retailers, you see a process as follows. The truck arrives with goods, and all the goods have been announced. So the company knows this truck will arrive. Then the driver of the truck has to offload the vehicle. So it's not the people of the company, no, it's the driver of the supplier who has to offload it. And this is typically palletized goods. The palletized goods are inserted onto a conveyor, and then they are brought automatically. So they're scanned automatically, checked automatically, and if okay, they are stored in a unit load automated warehouse. This is an automated storage and retrieval system, a high bay warehouse. Now, this is not something new. These systems are on the market already since the 60s. So this is, you might say, conventional automation technology. So the pallets are stored by these big cranes automatically. So when an order comes, you cannot retrieve a full pallet because customers do not want to have full pallets. They want to have a box or even a unit. So what happens is we have to destack the pallets. To destack them, we retrieve a pallet from the system, and then the robots destack them into individual sellable units. Each of these units is then stored individually into a system that can handle pieces of products or boxes of products, not full loads, just boxes or pieces. And typically AVSR systems are used for that, so shuttle-based systems. So now we have all the boxes stored. Now a customer order comes, for example, an order of a store. And the store wants to have a large quantity of products, but each product in a small quantity. So we have to retrieve all these boxes and then we sequence them in a way the customer wants to have them. And then all these boxes are stacked on a mixed pallet by a robot or a mixed roll cage in the way the customer wants to have the products. So completely customer specific build of the pallet or roll cage. Now this pallet, when it's full, it's stored in another buffer. And this buffer is again an ASR system, so an automated storage and retrieval system with cranes typically. And it sits there until the truck that goes to the store or to the customer departs. So when the truck arrives, all the loads are retrieved from this storage system. They're sequenced in the right sequence, the reverse sequence of loading, and they're brought to the truck. And typically they have to be sorted in some way. And that's also done by an automated system. The last step, that's putting them in the truck, that is still done manually. But apart from the offloading by the supplier and the loading, everything else is automated. Now, of these types of warehouses, about 40, 50 exist in the world, and the number is growing very rapidly. So in Western Europe, we see several. In the Netherlands, all retailers are currently moving into fully automated warehouses. In the US, you see several. Many other countries, we see these warehouses coming up. And why is it that this technology is now going so fast? That has to do with this new invention, which is only 10 years old, and that's fully automated stacking of mixed pallets. And this has been made possible due to very smart stacking techniques, smart robots that can stack mixed pallets and mixed roll cages automatically. And this is one of the first systems, this picture. So you see it's not just a robot. This is basically a combination of pushers that can push forward, that can lift it a bit, can move sidewards and just stack things on top of each other. But you can also do it with 5-axis robots like this one. So this is also a possibility. So this technique has become available at an affordable price, and this has made it possible that all these companies now have started stacking things automatically. However, even although there might be now 40, 50 of these warehouses, still the major applications can be found only in retail. And retail has some particular properties, like particularly in grocery retail, we know that customers will order grocery for a long term after now. So they have deep pockets and they have long-term perspectives in grocery retail because the payback time of these systems is extremely long. So you have to think of decades before you can earn it back. And you need to have very deep pockets to earn back such investments. So the payback times are really long. So that means that most companies cannot afford to invest in these types of technologies. So what technologies can you choose from if you don't want to automate completely? Well, you can automate partially. So part of the system can be equipped with robots. One of the systems that companies can use are the AVSR systems, autonomous vehicle-based storage and retrieval systems. So in this picture, you find them here. So you can just buy a small part of this system and then do it at much lower investment cost. So here are some examples of companies that supply these types of systems. So we have the traditional systems. These are the systems that use lifts. So this is a lift, and the other things are shuttles. So we have a lot of shuttles retrieving small loads stored in bins or maybe on pallets. And then the lift brings them down to the ground floor, and from there they can be transported to a pick station. So these are all parts to picker systems. Goods to man, if you want. So these shuttles in combination with lifts bring them to the picker. And many companies supply these types of systems. The first one was Savoie, that's a French company. And the system they came up with, I think it's now about 15 years old. And also the first literature on these types of systems is now between, I would say, more than 10 years old. And by now you find suppliers all over the world who supply these types of systems. There's a new generation of systems where we no longer need lifts. So this system needs lifts, but you can also have systems with rack climbing robots. For example, andOperations or OPEX or Exotech. So there are multiple companies now offering rack climbing robots. And here you see an example of that. So these are the systems we have studied. We started with Autostore. This is a picture of Autostore. So let me explain you how Autostore works. Skip the beginning. Okay, I think the idea is clear. So how does it work? Well, basically we have a grid like you see over here. And on top of the grid, we see these small robots, these red robots. And in the grid, we have stacks of totes. So these gray things here, they are totes stacked on top of each other. And then grouped at the perimeter of this storage system, we have workstations, and they are split in pick stations and replenishment stations. And you can group them at the perimeter, but you can also have them in the middle if you want. So you can basically have any type of layout with these types of systems. So if you need a product, then what happens, a robot drives to the stack, it takes out the top bin and the next one, so it digs out the right tote that you want to have. And the other bins are stacked temporarily on top of other totes, of other stacks. And then this bin that you require is then driven to the station, and then it's lowered by the robot. So the robot can lift and lower totes. And in order to dig out the right tote, it has to dig it out. At the workstation, you take out the item that you want to have, and then the remaining is picked up by the robot, and then the robot stores the tote again. So when we looked at these systems, and this was now about 5-6 years ago, I think, for the first time, we saw them for the first time. And then I wondered, how should you stack these totes on top of each other? Because it takes a lot of time to dig out the right tote. So should you stack only one product in a stack, meaning multiple totes of the same product? Or should you completely mix them, or maybe some hybrid form? And there is some trade-off, because if you stack them completely mixed, you have to dig it out. But the advantage is you can do with a smaller, more compact system. So your driving times of your robots decreases, but you are penalized because you have to now dig it out. On the other hand, if you have dedicated storage, meaning only one product in a stack, probably your system has to become lower, which means your system becomes wider. That means the driving times go up, but your retrieval time goes down. So there's a trade-off. And the question is, what is the optimal storage strategy? That was basically one of the questions we had. We had several other questions, but we wanted to answer that question. And so in order to do that, you make a model. In this case, you made a queuing network model. This is a semi-open queuing network model. And this is what a model looks like. So we have an arrival process. And here we have a queue with orders that arrive. So the orders arrive online, requests for retrieving certain totes. So the model is open for arrivals, but it is closed for robots. So what happens? An order has to be matched with a robot. So a robot has to pick up that particular tote that's requested. So this is a synchronization station, and this is where the robot and the order come together. Then the robot has to drive from its dwell point to the retrieval stack. Then the right product has to be retrieved. That is this node. And of course, this retrieval process, it depends on the policy that you deploy. If you have dedicated storage or shared storage, the retrieval process might look different. So it depends on whether it's dedicated storage or whether it is shared storage. In shared storage, you have to dig it out. So this is just, you might say, an abbreviation for a more complicated process. After you have retrieved the right bin from the stack, you have to bring it to the right workstation. So we have, in this case, NW workstations, and with a certain probability, you go to one of the workstations. At the workstation, the robot with the tote has to queue. And when it's time to pick the item, so when you're next in the queue, next in row, the item is picked at the workstation, takes a certain picking time, then it has to go back to the storage stack, then it has to be stored, and then the robot becomes available again for its next job. So the system is open for orders, but closed for robots. So this is a semi-open queuing network, and we model it, we can analyze it using aggregation and a continuous time Markov chain analysis. Let me sketch you how this is done. So this is the network, what it looks like. So the typical trick to analyze these types of network is, first, you have to make the network a bit smaller. And there are some ideas to do that. The first is we use a property from electronic circuits, and this is called Norton's theorem. It basically means that you can aggregate a number of processes together into a so-called single load dependent server process. So it looks like this. So we shortcut this network, and then this is equivalent under certain conditions to this smaller network, which consists of only one node, but with a load dependent service rate. So it depends on the number of items in the server and the queue, the speed at which it operates. So applying this trick multiple times, you can even shrink it further, because we can also now do this for the other remaining nodes. So we have a second load dependent server, and then we can merge it into a smaller network. So this is the smaller network that remains, and this can be analyzed using the continuous time Markov chain on the state space. So the state space consists of 3 elements. So that's the number of orders in the external queue, the number of loads or vehicles in the first queue, and the number of loads or vehicles in the second queue. And this is basically the net number of orders, because it's basically the difference between the content of this queue and the content of that queue. So this one can become negative. So we can define the Markov chain on this state space, and then this is known from literature how to solve this. So we use the matrix geometric method, which is developed by Gia and Hiragu in operations research in 2009. So the technique to do this is known. So this is what you can apply. It's quite involved, but okay, this is just idea how to approach it. So let me go back to what is the best strategy, dedicated or shared? Well, there's another thing you have to think of. If you stack dedicated, so this is a side view, this is of the stacks. So if this product arrives, you can only store it here in dedicated storage, but in shared storage, you can store it anywhere. So here you see the 4 products completely mixed. However, there is one thing we have to think of is that if you have multiple loads of a certain product, the space that these loads occupy differs in a dedicated storage system compared to a shared storage system. If you can share the space with all the loads, you basically need less space. So the total system size can become smaller if you share the space. So not just the width and length, but the total system size becomes smaller. You need less space to accommodate all the loads for shared storage. So you have to include that. Unfortunately, there is a nice formula to approximate the space that's required if you can share it with other loads, and that has been developed by Yu et al. In a paper in POM, in Production Operations Management, in 2015. They give a very nice approximation for the total amount of space given that you can share it with other loads. So it was a nice paper. And basically, this paper was important because if you look at earlier papers on storage space and travel time calculations, for example, the original papers of Hausmann, Graves, and Schwartz in management science, they all neglect the fact that if you can share space, that you need less space than when you do not share the space. And so they all neglect it, and the effect is really substantial. Okay, so we include that, and these are the results. So we have an optimization model, which basically minimizes the total annual cost of the system. And the decision variables are the height of the system, the ratio of length and width, the number of robots you need for a certain throughput, so the throughput is given. Also, the percentage of A products and the percentage of B products. We have different areas where we store the fast movers and the slow movers. And the total cost consists of the cost of all the robots, annual cost of the robots, the annual cost of the footprint, and the annual cost of storage space. And we have cost parameters for that. And of course, there are a number of constraints. One of the constraints is that we have a certain Pareto curve for demand. And the curve we assumed looks like this. So it's a very steep curve, but we tried it for many different curves, obviously. So this is an extremely steep curve, where only a few percent of the products is responsible for 80% of all the picks. But of course, you have to try different ones. So this is what we tried. And then the results look like this. On the horizontal axis, we have the throughput time of a load, including all the reshuffling required if you have shared storage. On the vertical axis, you have the total annual cost, expressed in millions of euros. And of course, you have two curves, one for dedicated storage and another one for shared storage. So we have an optimal, a minimum cost for both. And these are the curves for these two systems. What we can see here, assume that you want to have a maximum allowed throughput time of a load of, let's say, 150 seconds. We see that the shared storage policy, the optimal shared storage policy, minimizing this, has only a cost of, let's say, 0.6 something million, compared to a dedicated system which has more than twice the annual cost. So the conclusion is, shared storage policy is just, at least for this particular example, but also for many other examples, many other curves we tried, shared storage is just the best policy. So don't do dedicated storage, it's just not good. At least not in the examples we looked into. So I was very happy with this result, and then we went to practice and we started asking, how do you store the products? And then it appeared that none of the companies that I visited use dedicated storage. They all used shared storage. So basically we're studying something which is already known in practice. But to be honest, we started this already quite some time ago, and by now these systems have become very popular. But at the time we were starting this answer was really not known. But companies found it out very rapidly themselves. Okay, another example. These are the rack climbing robots. So rack climbing robot, this is a system that uses rack climbing robots. This is the OPEX system. OPEX is an American company, and they were the first with these rack climbing robots, I think. It looks like this.
Perfect Pick makes goods-to-person automation feasible for businesses that previously thought it was out of reach. At the heart of Perfect Pick's one-touch technology are patented iBots. iBots are intelligent wireless vehicles that race along tracks inside an aisle of dense storage racking, retrieving totes or trays of inventory and delivering them directly to an integrated workstation for order picking. iBots have 100% access to the inventory in their aisle and can be driven in and out of the system in a matter of minutes to dramatically impact throughput.
So the question we had is, when I first saw this system, this is about 8 years ago or so, I saw this system for the first time, rack climbing robots. And at that time, there were only very few implementations in the US. There were none in other places. And I thought, wow, this looks like a really a great innovation, because it doesn't require lifts. So if you look at the traditional AVSR systems,
Perfect.
like these systems, all these systems, they use lifts. And now there are a lot of systems that use lifts, but this system doesn't use lifts, and lifts are very expensive, and typically there are also bottlenecks in the system because they have to bring all the loads down from all the levels to the pick station, and also have to bring them up after picking again. So the lifts are typically bottlenecks. So you can have many shuttles, but typically you have only few lifts. So I thought they're probably better.
Perfect.
But are they really better? And in order to find that out, you have to compare, you might say, optimal traditional system with lifts. So optimal AVSR systems with lifts. And this is a traditional system with lifts. So we see shuttles at every level. These are the yellow things here. And we have lifts at the head of every aisle. And the lifts bring the totes that have been retrieved to pick stations. So in order to know which one is better, you have to compare the optimal AVSR systems with lifts with optimal rack climbing robot systems. So you have to make two models, optimize both for cost, and compare them. So this is an idea of the model for the perfect pick system. So you see here, we have a load and load station, and the robot climbs in the rack, and these are the aisles or the rack columns, and it descends in the rack column, does the picking, and typically there are double cycles. So you first store something, then you have to retrieve something. You try to store in the same aisle, and then you travel back to the pick station. One of the problems you can have there is there's a lot of blocking potentially, meaning if multiple robots need to pick up something in the same aisle, they have to queue on the top. So you have to incorporate robot congestion. And so we have different models with different congestion mitigating policies. And we evaluated these different types of models. So I'll skip the, so we did it with approximate MVA. Let me just immediately go to so this paper is published. It was published in Transportation Science, I think 2018 or so. This is the cost comparison of the optimal AVSR system with lifts compared to the optimal rack climbing robot system on 2 dimensions. So on the horizontal axis, we see the system throughput, the required throughput, and this is the required number of storage locations that the system needs. And of course, there are some assumptions with respect to the price of the robots and the shuttles and the lifts. And here we compare the perfect pick system with the AVSR system. So what you can see here in the purple area, the perfect pick system has the lowest annual cost. CPP stands for annual cost of the perfect pick system. Lower annual cost than a AVSR system with discrete lifts, lower cost than AVSR system with continuous lifts. Here, the perfect pick system is again the cheapest. Here, the perfect pick system is again the cheapest with the rack climbing robot. And only here, when you have a large requirement in system throughput paired with a very high storage capacity, it pays off to have separate lifts and not rack climbing robots. And this is intuitive because you have more resources and they can now work parallel. So yes, the congestion is probably so big for the perfect pick system that it pays off to spread it over multiple resources. So only here the annual costs for AVSR systems are lower than perfect pick. So this was intuitive. So nowadays, at that time, perfect pick was the only one, OPEX with perfect pick was the only one with rack climbing robots. But now you see more and more companies start developing alternatives for rack climbing robots, and they're becoming really more popular now also in practice. But conclusions with respect to these types of systems, AVSR systems with lifts or with rack climbing robots is, yes, there are a lot of companies that have now implemented them. So particularly Autostore systems and all kinds of shuttle-based systems we see now in practice, but still they are quite expensive. So the payback time is still quite long, not as long as for fully automated warehouses, but still they are quite expensive. So not really affordable for smaller companies. So smaller companies cannot just pay for these types of systems. They're too expensive. And they're particularly used in e-commerce. So most e-commerce retailers that I know already have these types of systems or are implementing them. So let me come now to some systems that are really applicable for smaller companies. So these are you might say, the poor man's robotic solutions. These are the pick support autonomous mobile robots, or short, cobots, collaborative robots. So these are systems that are a lot cheaper than any of these big systems that I showed in the previous slides. There are a lot of companies that supply these types of systems. So different types. First, the robot follows the person, like Fetch Robotics or Steel, or the person follows the robot, like Locus Robotics or Toyota. Then you have systems where multiple persons can work with multiple robots, for example, in zone picking. And we have another variant is where we can not only work with the robot, so the robot rides along while we are walking. No, you can also step on the robot and ride it yourself. So when you arrive at the location, you get off. So that's a separate type of cobot, you might say. So many different systems. Here you see some pictures. This is Locos robots. And here you see, this is Toyota, for example. This is Crown. This is, I think, no, this is also Crown, I think. So there are different suppliers of these types of robots. This is an implementation by Locus. So you see here a robot in the middle waiting for a picker. This picker picks something with the robot, then there's another robot waiting. So he picks with multiple robots in this particular case. And here you see an example of a robot which is a ride-on cobot. So we've been working on different papers, and none of these papers have appeared yet. So this is all work in progress. But let me sketch you some of the research we're currently working on. So the first paper we are working on is that's the following question. So this is a cobot where we walk with the cobot. So the picker walks with the cobot. And we are investigating whether it pays off to dynamically switch between a no zoning system and a zoning system. Let me show you what it is. So this is a top view of the warehouse, and here we see the robots, these small things, and here we see pickers. In a no zoning situation or parallel picking, so parallel picking, basically a picker walks together with the robot and picks an entire order in this warehouse according to some route. When the picker is done, the robot leaves the picker and the robot drives to a depot where the complete totes for the customers are taken off, and the picker continues picking with a new robot. So a new robot replaces the old robot and the picker continues picking in the reverse direction, for example. So the picker never has to walk to the depot. All the travel is done by the robot. In a zone picking situation, the warehouse is divided in zones. So the disadvantage of this system is that the picker still has to walk long distances potentially. Now, one way to mitigate this is to divide a warehouse in zones. So what happens here is the picker works in his or her own zone together with a robot, but at the end of the zone, the robot leaves the picker and the robot starts collaborating with the next picker to complete the order. The picker waits here and is met by a new robot, and it just continues picking in his or her own zone in the reverse direction. So the nice thing is, with these robots, we can basically give instructions to the picker to just pick with some robot. So we can completely dynamically change between this system and that system, or vice versa. So this was not possible in the past, because in the past zoning systems typically are organized by conveyors, and conveyors are static. You cannot change the layout of the conveyor. You basically have to break them down. But with these robots, you can completely dynamically switch between zoning and no zoning. And there are some pros and some cons of these different systems. So what are the pros and cons? So in a no zoning system, typically the robots do not have to wait for pickers. So you continue with the picker. So here in this system, the robot has to queue here and wait for a new picker. But the disadvantage is that the picker travel time becomes longer, and this system is just the other way around. So there is some trade-off here. So sometimes this is better, and sometimes this system is better. So how do we find out whether dynamic switching pays off? Well, we make a model that consists of two parts. The first part is we estimate the performance of the system for a given situation. So either for this system or for that system. We calculate the performance for a certain number of robots, a given policy, and a certain number of pickers. And we use that as input in a Markov decision model to decide when should we switch between one or the other. So we have basically this as a building block, and we use it in a dynamic program, Markov decision problem. So again, so how do we make the model for the first part? So we have to be able to estimate the performance of a picker together with a robot, or multiple pickers with multiple robots. And we have to model the process accurately to get the right throughput capacity of that particular system. So how does it work? Here we see a picker, here we see a robot. So the first step is that the robot and the picker travel to the first location together in parallel. And the one with the shortest time has to wait for the other one. Then, after the first pick has been done, they travel together, like this. So they visit all the locations that the order requires. And when the last pick is done, the robot continues, drops off the picked tote, and the picker continues with another robot in another order. So this is basically the process. The picker travels from the idle location to the first pick locations, waits for the robot. If the robot is not yet there, then they started picking together. Then the loaded robot leaves for the depot, and the empty robot finds another picker, and that process continues. So this is the process we have to model. So here they work in parallel. They work together. And we modeled it using a two-phase server. So this is how it works. So first, the joint travel, the individual travel of the robots and the picker to the first location is modeled as a setup phase of this server process. Then they start picking together, that's this part. Then the robot travels to the depot, and at the depot the robot has to queue because the order has to be taken off and packed. And then the robot becomes available and travels again for the pick processes. And basically this is then the network that we get. So this is what we can analyze. This queuing network with the very special feature of this two-phase server. This is basically the innovation in this type of model. So we can analyze this model for a single zone, so no zoning. And of course, we can also do that for multiple pickers. So not only for one picker, but for multiple parallel pickers. We can also do it for two zones. So what we see here, after the first zone has been finished, the robot can decide to go to the next zone, or maybe the order is already finished, and then we immediately go to the pack station, and after that, the robot is available for the next order. So the model for two zones is a bit more complicated than for one zone, and it's also a bit more complicated for multiple pickers than for one picker, and we can also extend it. So how to analyze it, we use aggregation, disaggregation type of solution. You can extend it to multiple zones. Analysis becomes really complicated, to be honest, but it's still doable. So what are the conclusions from such a model? Well, what we can see is in this picture, on the horizontal axis, I have the number of robots, and this is the order size. And the box indicated which one is better. So this indicates that no zoning is in this case 12.2% better than zoning, progressive zoning. This black box indicates that progressive zoning is better, and in this case it's 10% better than no zoning. So what we see is that basically no zoning is particularly good here, and that is when order sizes are large. And progressive zoning is particularly better when the order sizes are smaller, and also the number of robots has some impact. Now these results are intuitive, because if the orders are really large, then it does not make any sense to stop picking halfway and to give the order to another picker, because we don't save so much on travel for the picker. So it does not make sense to split the travel path in two, the route in two. But for small orders, we don't want to travel the entire warehouse. So it does make sense to try to minimize the travel for the worker. So in that case, we should zone. So these results are really intuitive. Is this clear? Okay.
Here,
No question. Good. So this is just the input. And so now we can analyze this model. Basically for different situations, zoning, no zoning, multiple zones, multiple pickers, we can analyze this model and we can come up with the throughput estimate of each of these for each situation individually. So now we include it into the Markov decision process. So we have here orders arrive in the system. We have a queue. We know the number of orders waiting, and we can analyze the performance of that system for the static situation. And what we do now is use it in a dynamic situation where we penalize the waiting cost per time unit to fulfill an order. So the waiting of order is penalized. And also, if the queue overflows, we have an extra penalty for that. So if we have to postpone an order to the next day, we also have a penalty for that. So this means that the costs of the policy are determined by waiting cost of orders, the postponement cost of orders, and also switching costs potentially. And we take a decision every time when an order arrives or leaves the system. This is the state space. We have the number of small orders waiting in the queue, the number of large orders waiting in the queue, and the current number of zones, which is 1 or 2 in the simple example. An action space is very simple. If we have 1 zone, we can change to 2 zones, or we cannot change at all. And if we have 2 zones, we can change to 1 zone, or we can remain as is. Okay, so let me skip all that. I don't think it's that interesting. So this is the total cost, consists of 3 parts: waiting cost, postponement cost of orders, and the switching cost. And okay, so let me just go to some example in view of the time. So we have a real case example, which is DHL. So DHL has not implemented this in this warehouse. So this is the layout of the warehouse. This is where the depot is. Here are some data of the warehouse. But they are studying it. So they have done a feasibility study together with a supplier of these robots, and they've come up with detailed estimates of what it costs, what it brings. And we use the parameters of that feasibility study, and they have still not made a decision to really use it. But we know all the data. So for a given situation, assume that the percentage of small orders is 0.55. This is what comes out for their situation with 8 robots and 6 pickers. You see that if the number of small-sized orders is large in the system, we basically should change, given that we are currently have only 1 zone. And this is obvious. You have to, so no zoning. So you have to switch to 2 zones if the number of small-sized orders increases. However, when the number of small-sized orders is small and the number of large-sized orders is large, you basically should remain where you are, which is basically no zoning. So these results are confirming what I already said. So this is all intuitive. So if you apply this in a dynamic model, and we use simulation to generate all the orders, and then we invoke the Markov decision process to take the right decision. So we have 4 different models here. No zoning for small orders, for large orders. So we have different models here, estimating all the throughput capacities, and we take the optimal decision. And this is what comes out. So we can basically distinguish 3 different regions. So in region A, where the small order probability is very small, we can see that the fixed policy of no zoning is basically already optimal. So what you see here is the difference with a dynamic switching policy. A higher line means a larger cost compared to dynamic switching. So here you see that the static policy of no zoning leads to the same cost as dynamic switching. So a static policy is basically optimal. And here you see that the static policy of zoning is optimal. This is when we have many small orders. But in between, in region B, we see that none of these policies, these static policies, is basically good. We always lose to a dynamic switching policy. A dynamic switching policy can improve both static policies. So conclusion is, in region A, where we have very few small orders, mostly large orders, for example, a store chain warehouse, we should not use zoning. In the region C, where we have a lot of small orders, like an e-commerce warehouse, we should use progressive zoning, static policy. But in region B, omni-channel warehouse, where we have both small and large orders, a mix, we should use dynamic switching. So dynamic switching pays off when you have a mix of small and large orders. And the improvement you get is about 8% cost reduction. How much time do I have left, Young Hong?
I think about 5 to 10 minutes would be good.
Okay, let me try to do it in 10 minutes. 5 minutes
Or
will not be feasible. I have to
yeah,
skip
or if you
subject.
talk a little bit longer, I think it's perfectly fine. Yeah.
Okay, okay, a bit longer, then I can also do topic number 3.
Okay. Okay, thanks.
So these are cobots. Cobots are really, this is what I talked about are cobots. I looked into modeling. How can you model that and see which policy is better? So switching or not. But very important is also the human, because these people have to work with these cobots. And the performance might depend also on the people that have to work with the cobots. And that's the second research question that addresses that part. So the question is, what is the best collaboration strategy for people together with robots, and for whom? So which type of people? What are the personality traits that determine the performance of the collaboration? So in order to do that, you really have to test this. So this is also not published, only a working paper, quite recent. So we have done an experiment with people together with robots in a lab. So there was a warehouse lab especially erected for this purpose. So this is the two scenarios that we tested. The first scenario on the left, you see the human is leading, and on the right we see the AMR, the robot is leading. So how does it work? If the human is leading, basically this order picker with the orange vest, he has a wrist-mounted terminal where he can see what he has to do. So he walks to the location and the robot follows him like a dog. The robot contains the tote in which the worker has to pick the items. In the right picture, the robot has a screen mounted on it. It's basically the same screen that the picker would wear on his wrist, telling the picker where he has to pick. So in this case, the robot is leading and the human follows the picker, follows the robot. And the robot is telling the picker what he or she should do. So two scenarios, the human leading versus the robot is leading. And you can already see there's a difference in attitude of this particular worker. It looks like he's a bit more bored with the second way of operating. Let's check what the differences are. So we have a number of research questions. So we look into different dependents, like what is the system performance, total productivity, but also accuracy, so errors that are made. But we also look into human performance, and we also look into things like task satisfaction, self-esteem, and robot efficacy. So I'm only going to talk about the first part, the performance, productivity, and accuracy. This is the setup of the experiment. Everyone had to do 3 runs. 1 manual run without a robot, just with a pick cart. And then 1 run where the person was leading, and another run where the robot was leading, or the human was supporting, in a random sequence. Each experiment took 20 minutes. And in between, we got instructions, demonstrations, test runs, etc., etc. And also had to fill in some questionnaires. To cut a long story short, these are the results. This is a linear mixed effects model, because we have to look into basically also effects explained by the person, by the personality. So you have to look into mixed effects models. And here you see the effect of the human leading. So the base scenario is the robot is leading. The dependent variable is the total number of order lines picked in 20 minutes. We see that if the human is leading, we pick 5 more lines in 20 minutes on average, compared to when the robot is leading. So humans leading lead to higher productivity. That's what we already suspected from this very short video. Human leading is more productive. Okay, but now let's look into accuracy. So this is errors, negative monomial mixed effect model predicting errors. Errors in 20 minutes. And now we see that, yes, human leading leads to more productive systems, but it also leads to more errors. 0.6 errors on average, more in 20 minutes compared to the robot leading. So yes, we are more productive, but we trade it off against accuracy, potentially. So this is also an interesting conclusion. And there's also a trade-off with the personality. So if we look into the interaction effects of personality and the human leading. And the personality in this case was measured as prevention focus of the worker. So what is prevention focus? It's basically from goal setting, not from goal setting theory, from regulatory focus theory. It tells how people try to achieve their goals at work. And basically we can discriminate two different types of ways and people can try to achieve goals. The first one is called promotion orientation, which basically means people try to achieve the goal by directly going for it. And this contrasts with prevention focus, where people try to achieve a goal by preventing anything that can lead to abstain from reaching the goal. So we try to mitigate risks by trying to achieve the goal. So this is called prevention focus. And here we looked into the interaction of human leading and prevention focus, and we can see there are some significant effects. Let me sketch you what the effects are in this interaction plot. So here we see that on the vertical axis, this is the time it takes to pick a line. So higher line means more time. So this is not good. Lower line is better. So we can see that if the human is leading the robot, indeed it requires less time compared to when the human is supporting the robot. So when the robot is leading, so left dots are lower than the right dots. But we can see that the difference between the dots is much smaller for people with a high prevention focus compared to people with a low prevention focus. So this basically means that the detrimental effects of a robot leading are completely mitigated or largely mitigated by prevention focus of the worker. People with a high prevention focus don't suffer from robot leading or robot following. They don't care. So this is interesting for managers to know that people, different types of people, might really respond differently to robot leading or robot following. So this is an interesting conclusion. And obviously, I have to admit, there is a ton of work more to do in this area. But this is just the first paper. In view of time, I skipped this one. Very interesting also. I would say this is really the poor man's robot. Looks like this. Very popular, I can tell you, because companies have to buy these trucks anyway. If you pick from pallets, you have to buy these trucks. And what we try to look into is, does it pay off to decide the point where you have to stop in an optimal fashion? And indeed, it does pay off. It leads to substantial savings compared to where you just leave it to the picker where to step off the truck, or where you determine it optimally. Okay, let me just skip that. So conclusion for these types of cobots is this is indeed affordable automation. Companies have to buy these trucks anyway, and they are not so much more expensive. It's also scalable. So you can buy a small number initially and then gradually expand the number of robots over time. It also can make the work of order pickers more attractive. But of course, it's still expensive, but affordable. So I had another part on robot sorting systems. I think this is also very interesting, but in view of time, maybe I should just skip all this because I already went 5 minutes past the time. By the way, I just want to say one thing about it. These robot sorting systems are basically a Chinese invention. So the first systems I know of were spin-offs of Hong Kong, no, not Hong Kong, of Wuhan. What is it called? HGUS, it stands for Huangzhou, whatever. Anyway, the University of Wuhan, I had some PhD students there, and they knew people who started this company, and now you see multiple of those. So robot sortation, very interesting also, and we have just published a paper in Transportation Science on it. More will follow. Okay, so I just skip all that. And by the way, they're also cheaper than classical sortation systems. That's what we also found out. So optimal robot sorting systems can be cheaper than optimal traditional cross-belt sorters. Okay, so let me wrap up. So I think there's a lot to do in robot systems. I just picked out a couple, but there are many more. By the way, what I did not touch on is Kiva type of robot systems, because there are now dozens of researchers focusing on those type of systems, so I thought, let me skip those. So I just treated a couple of less well-known types of robot systems. So they have great benefits, and they will influence practice and also research. However, there are a lot of very expensive systems that will still take decades before they become mainstream. So in the most warehouses, I will see people working together with robots. If there is automation, these will be the dominant type. People working together with these robots. We cannot fully automate the warehouses. It's just too expensive. And that means that there is a lot of room for research. So the room for research is the following. You can look into how to deploy these types of robots, how to control them, how do they impact performance, but also how do people collaborate with these systems? What determines the joint performance? And there's still a lot of work to do in this area. So that's what I wanted to say. I hope this sort of was interesting for you. It's interesting for me. I've become very enthusiastic about this topic. There's a sea of research to do, and I will continue doing that for a few more years at least. Thank you very much.
Yes, thank you very much, Professor de Koster, for the very interesting talk. And then I think all of us have learned a lot about the recent development and also the research on robotics in warehousing operations. So we have received some questions. For those who are interested in asking questions, please feel free to use the Q&A function on Zoom. So please tell us your name and also affiliation. So we have the first question from Nicole Schmidt from University of Ghent. So first, Nicole wished to thank Professor de Koster for this very interesting presentation. Nicole has the following question. So you assume some parameters for the investment cost. When comparing the efficiency of two different types of robotic systems, as described in the second paper, how confident are you about your findings, knowing that technology costs may change? Thank you.
Yeah, it's a good question. And of course, all the results we have are contingent on estimates of cost or other parameters. And costs come down. That's completely true. So costs change in the future. What I wrote down in these papers is contingent on the numbers. And of course, the curves will change when the costs change. For example, let me share my screen again. In the last picture here, I have a comparison of cross sorters, and these are the robot sorting systems. The orange and the blue line are the robot sorting system. This is a traditional cross-belt sorter. So this is contingent on the price of a robot. What you might notice is that the price of a robot is only 20,000 here. In the earlier papers, I assumed 40,000. So if the price of the robots come down more, you might expect that they will beat cross-belt sorters even for a longer range. So what will happen is that the intersection will occur at a much later point. So cross-belt sorters, they will beat cross-belt sorters even more than they already do with 20,000 euros. So yes, the costs come down, but still the costs don't come down that fast. What has happened is another change, and that is many of these robot suppliers have been bought by retailers recently. For example, Kiva was bought by Amazon Robotics, and this has made it possible for Amazon Robotics to basically use Kiva robots at the procurement cost, and the procurement costs are much lower as the sales price. So the sales price of a Kiva robot might be 40,000 euros, but the procurement costs are only a few thousand euros. So that makes it affordable for Amazon to equip all its warehouses with these robots. And this example of Amazon has been followed by a couple of other retailers. For example, Ocado has now its own robot system. Magazino was bought by Zalando, and there are other retailers, big retailers, who have bought these robots. So this brings down the cost enormously, and this expedites the implementation in practice. So you're fully right. The results are contingent on parameters, but the methods, of course, are still valid, and you can just apply them with other methods, with other parameters. Sorry.
Great. Yeah, thank you very much, Professor de Koster. So we have the second question from Laurie. Thank you for the insightful talk. We know that some airports start to use AGVs for baggage handling. I'm wondering if you have any comments on this type of application, pros and cons as against traditional conveyor belts.
Yeah, it's a very general question, but basically it's you might say a sorting system. And the big advantage of using robots is that the building becomes smaller. Sorting system typically requires a lot of space for all the sorters. And you should have to have a certain length. The sorter itself requires a lot of space, and space is typically the dominant cost. So you can sort items on a smaller area, and that's one of the big advantages of using robots. The robots themselves are still quite expensive, around 40,000 euros or so in Europe at least. That's the price that you pay. But still, you save not only cost in equipment, but also cost in the building, and that makes that you earn it better earlier. That's also one of the advantages when I compared it with the cross-belt sorters, is the building becomes cheaper with robots. And of course, the other advantage is you're much more flexible. A fixed sorter is static, and you cannot easily move it. So it's there to stay. Whereas robots, you can just program a different destination, and as long as the travel path is available, it can get there. So the requirements in infrastructure are much less for robots, and they're much more flexible. So I think this is really something that's going to that we are going to see more in the future. So even in Rotterdam, which is a very small city, our airport uses these robots, these baggage sorting robots. I have to admit it's a pilot, but more and more will show up.
Yeah. Thank you very much, Professor de Koster. So we have the next question from a team from Hong Kong U. So thanks for this very interesting and insightful talk. The idea about the cobots is very exciting. So I wonder if, I think it's typo, whether it's a mature or how mature and prevalent this technology is.
Yeah, also a very good question. So there are different types of cobots. The technology where cobot walks, where a worker walks with the cobot, is still a bit immature, I have to admit. So the implementations, I know, you still need software engineers to tune it. But this is for now. In 2 years, this is mature technology because it really goes fast and there are many implementations on their way. So yes, of course, if you now buy it, you probably are a guinea pig. But if you wait for a couple of years, this is mature technology. This goes really fast. The second one, the ride-on cobot, that's already mature technology. Although the technology is really new, it's mature and it works at full speed already now.
Right. Yeah, thank you, Professor de Koster. He has one more question. So does the proportion of human pickers and robots matter in your analysis?
A very good question also. And this is also the crux, because the more robots you need per picker, well, the less attractive it gets, right? So you want to save on pickers and you want to save on robots. And you need to have the optimal ratio of the two. Now the robots, if you have a robot working together with a person, you need more robots than people. Why is that? Well, first, the robot and the person work together, but the robot has to do additional tasks. The robot has to pick up a new order somewhere, so totes, and it has to deliver complete picked totes to a packing station. So the robot has additional tasks. So you need more robots than picker. What is the optimal ratio? I would say you need about 20-30% more robots. But it depends on the strategy. But in most companies I see you need at least 20% more robots, at least. And it depends on a bit on which strategy you follow. What is the optimal ratio?
Yes, thank you very much, Professor de Koster. So we have the next question from Suyan Zhong at University of Exeter in the UK. Thank you very much, Professor de Koster, for the interesting research agenda introduction on warehouse robotics. I have a question regarding cobots. I have read several of your papers in integrated planning for different successive processes in a warehouse. Would you think the dynamic zone or parallel picking switching can be combined with other planning problems to improve picking performance, such as how to generate a most appropriate pick list to cater to the zone or parallel picking strategy? Many thanks.
Also a great question. Now, to be honest, this system is not used in practice. We just came up with, wow, it's possible now to dynamically switch. We still have to find the first company willing to use this ID. But in general, you can now have an optimal collaboration between pickers and robots. So yes, of course, it's possible to assign the right picker to the right robot with the right order. Yes, that's possible. You can even make behavioral models like this person is better in doing this or that and match the right person with the right robot in the right order. This is possible. To be honest, this is basically a virgin research area. There is very little research on this. So I have an old paper in eJOR, well, old, it's from 2019, I think, where we looked into what are the skill profiles of pickers, and maybe we can match the right order with the right skill profile in a static environment. But this is completely dynamic, so it adds an extra dimension to it. I would warmly welcome this type of research. It's completely new, unexplored, and it will definitely bring benefits. I just don't know how much.
Okay, so we have, I think, 3 more questions. One from Xiaowei Li from Beijing Jiao Tong University. So nice to meet you, Professor de Koster. Thanks for your wonderful lecture. So Xiaowei is very interested in this research topic. He thinks that although the robots are widely used in practice and they can improve the efficiency of the order picking system, our human remains indiscernible for certain operations. When facing plenty of tasks, human may feel tired or bored. So there are many human factors may affect the efficiency of the system. So the question is how to incorporate human factors into model in such a hybrid human robot or machine order picking system. And the pickers are heterogeneous, how to deal with it. Many thanks.
Ooh, yeah, the question is, of course, it's to the point, but very difficult to answer because I just don't know the answer, to be honest. I think it can be done, but you have to tackle one problem at a time. So don't try to put in everything, right? So when it comes to behavioral factors, I think it should start with empirical research, because in order to make the right models, you have to know how people really respond and what are the difference between people that really matter. So you have to study first this type of response in empirical research, and then the output of that empirical research can feed into modeling approaches, not the other way around. Don't assume away. Assuming away doesn't help that is really what you want to tackle, right? So you have to start with empirical research and feed that into models. How to do that? Well, to name the example of the paper I just mentioned, which was published in eJOUR, we had first an empirical model. We tried to forecast what is the expected behavior of someone when I would give him this type of order. So based on historical information, we just analyze the data. You can try to make a forecast, a prediction about how people would respond if you give them certain type of work, and use that in an optimization model. So basically you have a combination of regression type of models or machine learning type of models feeding into optimization models. But the first part, the empirical part, should always be on data, real data, not based on, you cannot just assume in an optimization model that people would respond in a certain way. You have to ground it on something. Is that a sufficient answer?
Yeah, it's perfect. The next question from Siying Yang from BJTU. You have collaborated on some papers on joint order sequencing and rack sequencing in such systems. What will be the future developments on this topic? Thank you.
Sorry, the question is not completely clear to me. Rack sequencing or?
Yeah, joint order sequencing and rack sequencing. And then, so what will be the future development of this topic?
I'm not sure whether I understand what rack sequencing is.
So Siying, if you can further clarify, then we may come back to this question maybe. Then we may
define what rack sequencing is. I don't know what is meant with that.
Yeah, so maybe Siying, you can further elaborate on this, and then so maybe we can move to the next question, and then to see Siying would come up with some more elaboration. So one more question from Nicole Skimmett. So would you say there is a conceptual difference between a bucket bridge and the cobot picking with dynamic zoning?
Yes. So to be honest, again, a good question. Bucket brigade, of course, also has dynamic zoning in a session, in a way, right? Because the zone continuously adapt. What we did is we have a simpler version of dynamic zoning. We just have no zoning, or we have two zones. And when we have two zones or three zones, you can also do it with three zones, obviously. But anyway, when you have three zones, the boundaries are prefixed, right? So there's not like dynamic boundaries. With bucket brigades, the boundaries are basically dynamic. So that's a big difference. Of course, this is also possible to apply this model with dynamic boundaries, but that would require basically a different model. And so with the current model, we cannot do that. It is probably possible to investigate that, but it would require a different paper. But it would be very interesting to investigate that. We have also, by the way, we have done an experiment with comparing different order picking methods, looking into what is the interaction between behavior, order picking methods, and incentives, and compared no zoning, fixed zoning, and zoning with dynamic boundaries, or basically bucket brigades. And we found that bucket brigades basically does not perform very well. It depends a lot on the types of people. So there's also an interaction with you might say, personality of the person.
Great. Thank you, Professor de Koster. So the next question from Bo Shui Zhao, a PhD student in KU Leuven. So thanks for your interesting talk. For the e-commerce industry, if automated warehouses are feasible, what is the expected storage cost of each package in Europe and China? Because of the different labor costs in different regions, so what region do you think this is most likely to achieve automated warehouses?
The question is completely right. So, of course, the solution will heavily depend on two key parameters. Number one, cost of labor. Number two, cost of land and, well, cost of land and the buildings. If you go to the US, land is in some areas, not all areas, but some areas, land is cheap. You can come up with vast buildings. If you go to go to Hong Kong, warehouses in Hong Kong, they're tall, multiple stories. Why is that? Well, come on, land, the cost of land. You have to build vertically. No one in, you might say, the Midwest in the US would consider building a warehouse like that. It's just too expensive, right? So you get completely different designs when these two cost ratios change. Don't fully automate when labor is cheap. Full automation can never beat it. When there's abundance of labor, when labor is cheap, don't automate. So the main reason that companies automate is not because it's cheaper. As I said, the major reason is different. The major reason is no space. We have to do something in a very small footprint, or labor is not available. That's why companies do this.
Right.
Not because automation is cheaper. That's not the case. It has to do something with the cost of space and labor, but where it is available, not the cost.
Yeah, thank you, Professor de Koster. We have the final question from Professor Guoqing Zhang from University of Windsor. Thank you for the comprehensive review and very informative talk. How does the layout affect the performance under the three different levels of automation? How to decide the layout in shared space at each situation to improve the performance? Can dedicated policy provide better performance than shared space policy in some cases?
Yeah, so I have the impression this refers back to the Autostore model I presented first, where shared space requires less, shared storage space requires less total space, and where dedicated storage space requires more total space. And I have the impression that it refers to which of the two should we go for. So if that's the question, then my answer would be this decision only makes sense when you have multiple loads of the same product. If you have only one pallet of every product, it's a non-decision, right? Because we are not talking about how to share the space of all the individual loads of the product. Every product needs just a space anywhere. So the total space is not affected if you have only one pallet. This only becomes a problem or an issue when you have multiple loads per product on average. So a larger number of loads. Then this becomes an issue. So if you have a larger number of loads, then the answer is, well, this is also what we studied in this paper published in Palm. The optimal system is, storage system is, go for ABC storage. Just 3 storage classes. It's very robust, and it appears to be not optimal, but close to optimal in nearly all cases that we studied. So it's only epsilon away, you might say, from the optimal configuration. So shared storage in multiple classes. 3 is enough. And by the way, this is known in practice already since decades, but it was proven only in 2015.
Right. Okay, so I think Ziying just came back with the some clarification. Our hierarchical planning concept of for Kiva warehouses can be concluded as order selection and assignment. Picking station scheduling determines the assignment of orders to batches and their processing sequence at a picking station and assigns racks to satisfy the demanded SKUs. 3 would be rack assignment problem, RAP, assign each stopover of racks storage position. And 4, robot assignment and path planning. So the question is the combined research direction of the first 3 points.
So if you look at Kiva systems, indeed, there's a lot of different decisions that have to be taken. It's even more than the 3 that are currently mentioned. So there are many decisions and they all interact. And what you have seen in so far in literature is all these decisions are studied in isolation. And well, in the best case, sometimes 2 decisions are studied. We published a simulation-based paper, so not a modeling paper, in operations research perspective, where basically all these decisions are studied are studied jointly in a real system. So this is a very large system where we included all the inventory of all the products on all the pods, and we can show what the impact of all the decisions is together versus in isolation. Studying decisions in isolation is not good. That's the general conclusion. There's a really big performance gap compared to when you study them combined. If you optimize it combined, it really brings a lot. Having said that, there is currently no paper that does that. To be honest, I have one paper submitted, but all the papers I've seen so far study these things in isolation, or at most 2 at a time. And that's not good research. So you can come up with optimal solutions which are far from optimal if you study it in a larger context.
Right. I think we have, okay, so you have your seminar is very popular. So one final question from Bo Shui Zhao, and the question is, automated warehouse involves queuing theory and sequencing or scheduling model. Is this similar to the appointment scheduling theory in healthcare fields?
Oops. Repeat the question, please. This is difficult for me. I have to relate to completely different subjects. I have to think. Can you repeat the question?
Is it similar to appointment scheduling theory in healthcare?
Well, in most, you might say, scheduling environments, you can make a sort of hierarchical decision, right? And this is true in healthcare. So capacity determination, assignment, or grouping, assignment. So these are typical hierarchical decisions that are used in many environments, not just healthcare scheduling. If you go to production planning, you see similar things. So the general ideas that we see here are applicable very widely. And we all know that doing things sequentially is not optimal, but at least we can do it. We can tackle the problem. We can decompose it. And by the way, this is also the way how it's done in practice. We should not mix long-term decisions, capacity decisions. We should not mix that with operational assignment decisions, for example. Please do that separate because they run on a different horizon. So it's also good practice to decompose them. We also know that if you would study it in an integrated fashion, you get better decisions also. That's also what we know. So the similarity is there. Of course, there are a lot of details and individual components of these individual models that are used for the individual decisions, but the similarity is there. And in that respect, we can definitely learn from other fields. And this is also one of the difficulties, of course, in every subject. Researchers in every subject invent the wheel themselves again and again. So because they are not knowledgeable about what is done in other related fields. And even though there are differences in detail, there might be large similarities in the approach. But I do not know enough of patient scheduling or appointment scheduling to give more details. I'm very sorry.
Yeah. Thank you very much, Professor de Koster. I'm sure the participants were very excited about your seminar, and then so that's why we receive many questions. So we learned a lot today. I wish to take this opportunity to thank you again for your great support to be a distinguished speaker. And I also wish to thank the participants for your continuous support. So I hope that after the pandemic, we would be honored to invite you to visit our department and then to have a closer interaction about warehousing, operations, and then also some future direction. Before we close the seminar, I wish to do again some promotion. So for our upcoming seminar, so the next one would be on June 24th. And then so if you have, if participants, if you wish to stay updated, with our seminar series, please feel free to visit our website and then to subscribe to our seminar. I think that's all for today. So I wish to thank again Professor de Koster for the very interesting and insightful seminar. So we all learned a lot. Thank you, Professor de Koster.
Thank you very much.
Yeah, thank you
all
so much.
for your attention, and goodbye.
Yeah,
Thank you so much.
goodbye. Professor Huang.
Thank you, De Koster.
Yes.
Bye.
Thank you.
Bye-bye.
Bye.
Bye.
Yeah, and also thanks to all the participants. I know in Asia it's late evening, so thank you for your great support. See you next time.
Bye.
See you in Hong Kong or some other conference, Professor de Koster.
Right. Maybe next year again, right?
Yes, please. Okay.
Bye.
Take care. Stay safe.
Bye.
Bye-bye.
Okay, bye-bye. Thank you.
谢谢 ，Thank you，辛苦了，辛苦了，早一点休息。
大家啊，
好，拜拜
bye，good night，
，Good night。
bye，拜拜。